Okay, I think we're 9 o'clock now, so I think we're gonna make a start. Good morning, everybody. Welcome to the second day of the Gaussian process summer school, and we have a day ahead of very interesting lectures. And the first lecture is gonna be on scalability of Gaussian processes by Dr. Zhenwen Dai, who is a research scientist at Spotify. So thank you for being here, Zhenwen.
Yes, thanks, Mauricio. Cool. I guess I can get started. Hi, everyone. It's my pleasure to talk about the scalability of a Gaussian process. And let's go straight ahead. In this lecture, I'm going to start it really slowly about discussing what is the scalability issue of Gaussian process. We will go through the details about the Gaussian process formula you have already seen yesterday and seeing their complexity and what causes the scalability issues. And then we will walk through a few common methods we might use to tackling these problems. The method I will talk about it here will be more or less those basic methods. Many state-of-art methods are based on this kind of technology described here. So ideally, we will go through some numerical solutions for us to speed up the directly the calculation, and we're also going to look into some model or inference approximations for allow us to further scale up the inference, and lately we will talk about how we can do mini batch training, which allow us to further scale up to handling the inference with a large data set. And in the end, if we still get time, we may discuss how to draw efficiently approximate the function samples from Gaussian process, because there has been quite a lot of interest of using Gaussian process samples for some downstream application like Gaussian process, Bayesian optimizations, and that might become handy to knowing how to do it. So let's get started. First, let's recap Gaussian process regressions. This is really the standard formulas you probably has already repeatedly seen from yesterday's lectures. So just for like a line on the notations, let's go through it again. Typically, when we're talking about the Gaussian process regressions, we're usually looking at a set of input and output data set we denote the output as a y. Usually, we are assuming that they are being a scalar. If it is vectors, there are some other ways of modeling it. In this particular case, we assume it's a scalar. We have a capital N of them, numbering from y1 to yn, and we group them as a vector, so we denote it as the vector notation y. And as input, we also have the corresponding input locations for each of the n data point. And commonly, this input is actually a vector, but in this particular case, you see in the figures, they are scalars. For better visualizations, we denote the corresponding input as x1 to x capital N, because normally each of them are vectors, so that we stack each column vector together, and it forms a matrix, which is an n row, and usually we denote the input dimensionality as a q, so it's an n by q matrix. And for a regression, for Gaussian process regressions, we are typically considering two parts. First is a Gaussian process part. For a finite number of observed data, as we can see here, for example, capital N of them, we write down the Gaussian process as a multivariate normal distributions, which we use F usually to denote like the noise-free observations of the data. And without usually we do not assume a particular mean function for the Gaussian process unless we have specific domain knowledge. So in this case, we're assuming the mean of Gaussian process will be constantly 0, prior mean, and the covariance of the Gaussian process being a covariance K, capital K, which is calculated based on the set of a point. The set of an n point will result into an n by n covariant matrix. So these forms are multivariate normal distributions, and P of y given f is then we call the likelihood or the noise distributions. We should usually assume that the observed data y is the mean is a noise-free observation f, and on top of that we have a little Gaussian noise, which is the amount is a sigma square I. In this particular case, sigma square is a constant with respect to the input, so that for different location in the input domains, the noise variance is the same. So this being the typically the most simple Gaussian process regression model we will have, and let's look at the computation details of such a Gaussian process regression model. First, what is actually happening when we talk about a fit of a Gaussian process? What do we mean by when we have a data set and apply Gaussian process? We usually mean two tasks we need to do. First, we have to determine the model hyperparameters of the Gaussian process model. In this particular example, for simplicity or for a lot of cases, real use cases, we only do a point estimate. I just want to mention it is also possible to do a Bayesian inference over the hyperparameter, but that will be much more complicated. With since we're talking about scalability, so in these lectures we will mostly talk about the cases we're doing only a point estimate over the model hyperparameters. In particular, in these cases, we denote all the model hyperparameter as a theta, which involve the sigma square, which is noise variance, and any hyperparameters inside the covariance matrix calculation inside of K. And a maximum likelihood estimate of the hyperparameters usually can be written as let's find the set of hyperparameters theta that gives us the highest log likelihood. From the previous equations, we marginalize the noise-free observation f because both are Gaussian, so that we can result into directly a multivariate normal distribution of the noisy observation y, which is zero mean and k plus sigma square I. And then after we find an optimal set of hyperparameters, and again condition on the observed data, we want to do something about the model. So typically the things we do is that we want to make a prediction at a set of unknown data point, or we call it tested locations. The set of test locations are often denoted as x star. It can be multiple point, or it can be a single data point. In this case, we write a notation for a set of different data point x matrix x star, and this is the prediction distribution for a noise-free observation f star located at the set of point x stars. The resulting equation is like this. You may find this equation familiar because this is just happening over and over again. This is basically a conditional multivariate normal distribution, and we will dive into a bit more details of calculation of these things in a second. But just for now, this is the equation we will use to make a prediction conditioned on the estimated covariance matrix and the hyperparameters. Okay, how does each of these steps happens? Let's go into one step more details into how the calculation is done. Just to quickly recap about how the calculation of the covariance matrix K is actually being done. We already said that the covariance matrix K is M by N covariance matrix. The way it is calculated is by doing evaluating a pairwise covariance matrix function, small k functions, over every individual pair of the input data. So for example, the diagonal ones are kx1, x1, x2, x2 until the xn, xn, and the off diagonal are the corresponding pairs of input locations. And we evaluate we apply these kernel functions for all these individual pairs of input and result into an n by n covariant matrix. A common choice of the kernel functions are, for example, exponentiated quadratic one is basically taking an L2 distance between a pair of location xi and xj, and then divided by 2L square L. We often call it a length scale, determine the smoothness of the function, and there's a gamma in front to control the variance of the Gaussian process. But anyway, it's quite easy to see the computational complexity of calculating such a covariant matrix K is n square Q, because we have to calculate for every individual pair of the input location, which result into a n by n calculation, so it's n square, and the Q is indicated the input dimensionality, because we have to do those L2 norm calculation or the squared distance calculations, which is linear with respect to the input dimensionalities. So the n square Q is the computation complexity for getting the covariant matrix K. By the way, feel free to stop me if you have any questions. I will run through these things, and sometimes it may not be very clear, so feel free to stop me and ask questions. After we seeing how to calculate the covariant matrix K, and the next things in order to do maximum likelihood estimate, we need to calculate the log likelihood of the Gaussian process, which we already previously seen is the equation of log of the multivariate normal of y with zero mean and the covariant matrix K plus sigma square I. And if we just look into how the multivariate normal density being written, and then you can very easily see, plug in any equation you can find on Wikipedia's or some textbook, you will find out it consists of two parts. First is a log determinant of the covariant matrix, 2 pi the covariance to be precise. And there's a second term is the quadratic of the is a quadratic form of the y transpose the covariant matrix inverse and the y. And numerically, if we try to implement in these equations in code, then the third alarm is what is actually happened. You will notice that the K plus sigma square I, we have an inversion here. Because we know it's a covariant matrix, so we will, instead of using those general purpose matrix inversion, we will use a specialized, or it's like dedicated matrix inversion technique we call the Cholesky decomposition, because that is the most numerically stable routines for inverting a positive definite matrix or covariant matrix. The way such a calculation happened is that we first calculate the Cholesky factor of this covariant matrix, which we denote as L, which is a lower triangular matrix. And the relation of the lower triangular matrix and the original covariant matrix is that the covariant matrix will be equals to the L and L transpose. And then if we plug in the L transpose into the second line, for example, on the right-hand side, we will resulting into a symmetry structure, and the symmetry structure result into an inner product with two vectors, and then we can rewrite the inner product as the L2 distance, which is basically, you can see it is like the L inverse Y, the vector, and then we calculate its distance. Note that even though here we still have an inversion notation, because the L is a lower triangular matrix, we can efficiently calculating this inversion L inverse Y by a special numerical routine called a back substitute. The computational complexity or the speed of such a back substitute is almost as efficient as a standard matrix multiplications. And also for the first terms, if we plug in the L transpose into the determinant, And then following some determinant rules, we will know it's like determinant L times determinant L. And because L is a lower triangular matrix, determinant of the L is basically the multiplication of the diagonal entries. And also we have a log in front, which becomes a sum of the log of the diagonal entries of L. And this part we can calculate it by the complexity of ON. And because this we say it's a back substitute, it's a complexity of n squared. And we know the Cholesky decomposition, the complexity is ON cubic. So that the overall computational complexity of this log likelihood calculation is ON cubic plus n squared plus n. And we just omit the n square and n. So we just say like the computational complexity of such log likelihood calculation is n cubic. So that is the complexity analysis. If we have the code, if we just write down the numerical code in NumPy of what we just said before, we can actually run a profile of seeing like how much time it take for toy examples to see like how each part of the calculation takes. This is exactly a NumPy implementation of the previous mentioned log likelihood. And I applied it to a really toy data with 1,000 data point and the input dimensionality being 10. And the second column shows is the absolute runtime of these functions in terms of millisecond. And the third column shows the percentage of the times across the different lines. You can see, so I highlighted with red are the most expensive part, which is significantly more expensive than the other part of the code. And it's unsurprised the Cholesky decomposition is expensive because we know it's an n cubic, and that is this line is basically doing the Cholesky decomposition of the covariant matrix. And also we notice another expensive part is the covariant matrix calculations. This have a high percentage of the computation time for two reasons. First is the complexity is still quadratic. It is not small. And remember previously in RBF kernel calculations, it involves exponential operators. The exponential operator has to be calculated for every individual entry of the n by n matrix, so that we're actually doing n square number of exponential operators. Each of them are quite expensive. And therefore, overall together, it actually takes quite some computational time. The other aspect of this is that the m of 1,000 data point is still relatively small. If we continually increasing the number of data point, and then the difference between a quadratic scaling and a cubic scaling then will start to reveal, and we will see the Cholesky will take a higher amount of percentage of a runtime, and the covariant matrix will take relatively less. Anyway, this is just to give an idea about how such a log likelihood calculations happen in code. And then we can do some further analysis based on our toy examples. We can actually, just based on the previous implementations, changing the number of n data point involved, and seeing profiling how long does it take for calculating that functions. I just did it for these examples on my laptop. For n equals 10, we have like 1.3 millisecond. N equals 100, I get 8 millisecond. And until I try the 2000, n equals 2000 data point, I have like a 0.76 second. And also, we know the computational complexity of this log likelihood calculation follow a cubic complexity. So what I did in this diagram is I do another meta-analysis. I fit a polynomial, a 3-order polynomial Gaussian process based on these 6 observations. And then we can see these points are quite nicely aligned, even though these actually are profile result from my laptop. It is still quite nicely aligned with a cubic scaling curve. And with such a fitting, what we can do? We can then use our meta Gaussian process runtime prediction function to predict what if we go into a crazy number of n. How long will it take? Say if we have for that just simple cases on my laptop, this will actually not be possible because we will first run into a memory limitation. Just for the time being, imagine on my laptop I have an unlimited memory, CPU memory, and then follow in the same runtime scaling. If I have a 1 million data point, one iteration of a log likelihood calculation will actually take about 3 years. That is the power of a cubic complexities, because even though 2000 data point, it looks okay, it is only take less than a second, but if we go 1000 like 3 magnitude higher, then it becomes totally intractable. So how can we deal with it? Of course, since we're talking about it, of course we don't stop there to accept the fact that it is so slow that we can only run our Gaussian process analysis with the limit of like 1 or 2000 data points. So there are actually literatures about how we can go beyond of those exact complex calculation to trade off some inference accuracy for better scalabilities. The first obvious thinking will be like, we know the cubic complexity comes from the covariance inversion. More precisely, it does actually come from this part, the y transpose k plus sigma square I inverse y. And we know there's decades of research of numerical linear algebra algorithms. There are for sure some numerical algorithms allow us to speed up the calculation by taking some approximations. Yes, that's totally true. That is actually leads to one direction of approximate Gaussian process, which leads to some computational speed up. Let's look a little bit closely about how it is happening there. Here I will only talk about the basic ideas, and the state of art algorithms are built on top of this kind of basic ideas. First, let's start with looking how the numerical approximation is actually done. Let's for the time being only consider one side of the cubic term, so that let's just omit the y transpose in front, because if we ever done this multiplication k inverse y, it will result in a vector. Then that multiplication is just an inner product, so which is really fast. So let's focus on this side of the calculations. And also for just the convenience of notations, let's denote the k plus sigma square I as a k hat. So and then from a numerical routine point of view, our goal is to find a vector v which is equals to the k hat inverse y. And we can rewrite these numerical routines into a linear systems by multiply the k hat on both sides, which result into a k hat v, and then if we move the y here, it becomes a standard linear system formulation. So k hat v minus y equals to 0. And further, we can represent the solution of such a linear system as a result of a cubic optimizations. We can say that the optimal, if we try to find the optimal v's, we are basically can say if we augment it into a quadratic system by multiply the the V transpose on the left-hand side, then it become a quadratic system so that we can find the solution of this linear system V star being the minimum, the argmin of these quadratic objective functions.
There's a question for you, by the way.
Sure.
It's I've just lost it. You can probably find it. Oh yeah, why not go for parallelization or GPU?
Oh yeah, good point. Actually for covering more content in this year's actually omitted the GPU and the parallelism part. I usually will talk about a little bit of it. I can quickly mention. First, Cholesky is Cholesky decomposition is not naturally parallelizable. There are research about how to parallel Cholesky factorizations, but because it still result into like those block matrix structure, it is fairly complex. So that means there's quite a lot of communication between the nodes that they are speed up, but it's not dramatically. And also, GPU is actually quite a nice thing to speed it up. With currently available standard GPUs, we can easily scale up. See, previously we can with CPU can easily handle at the magnitude around like 2,000 to 4,000. So that is totally manageable. And with GPUs, we can go it up to 13,000 is totally fine with a modern GPU like a Titan a few years back with like a 4 or 8 gigabyte memory. And one issue here with this GPU and the parallelism approach is that often if we look closely at these calculations, we often run out of the memory instead of computational time or our patient first, because one side we didn't talk about the spatial complexity of this simple algorithm is actually n squared. So that if we have a million data points, that means we will easily go into like the K, meg, gig, and the terabyte regimes of the storage, so that we are very quickly run out of memory. That's also limiting the use of the GPU hardware to do it, because every single GPU is have a limited memory. And also I previously say like the parallelization of Cholesky is quite complex, which result into such scenarios is you can find some. For example, a library to do cross GPU card Cholesky, but in general, the gain is not linear.
Cool, thanks for that explanation. That's great. Thanks.
Cool. Let's go back into our numerical routine, and yeah, of course, the naive way of solving this this quadratic optimization is just the gradient optimization, right? But that is definitely not the most optimal solution, because we know it's a quadratic system. There must be more efficient way of solving it, which is totally true. There's actually a literature about a method called the conjugate gradient method, which can very efficiently solve such quadratic system, especially the K is a positive definite covariant matrix. I won't go too detailed, but just give a little bit the flavor of what is happening. The way it solved the problem is to construct the final solution as some initial V0 guess, some initial guess of the solution. You can take like a zero vector or some random vector, and it will try to find the n, because it's an n by m matrix, so it's an n-dimensional vector, so that it will try to find the n independent, linearly independent vectors d1 to dn with the corresponding coefficient in front, so that the aim is to find a v star being written in such a form. There is some particular benefit of writing such a form, is because it can iteratively go through discovering those independent vectors one by one. Because actually those vectors is actually conjugate direction of the covariant matrix or the matrix K hat. This is on the right hand side is just the equations of this iterative conjugate gradient algorithm. I will only just describe some characteristic of it. First, it is iterative algorithm, so you can see it starts from V0, and every time it will update into a new version of a V. And the conjugate gradient, if we ignore numerical issues, it will recover the exact solutions after the n iterations, because from the previous equation, we know that the n-dimensional vector can be exactly written by, like discovered by n independent vector, because that span a n-dimensional linear space. And then, of course, if we iterate n times, that is not fast, because every iteration is n squared complexity, because every iteration you can see it involve in the many steps the K hat covariant matrix, so that these kind of calculations complexity are n squared. So that if we take n steps to get a solution, then we fall back into cubic. But the idea about the conjugate method approximation is that we try to solve, we try to result in the approximate solutions by taking the number of iterations much smaller than n, then typically a constant number, so that then we result into a regime to be the overall complexity to be n squared instead of n cubic. But then, of course, you would imagine the problem is that how many steps we take, like how good we can result in if we take, say, 10 iterations, how good we are. There's actually quite extensive studies about these scenarios. The outcome is that the numeric stability and the rate of convergence of a conjugate gradient method are sensitive to the property of the covariant matrix. In particularly, it is sensitive to the condition number of the covariant matrix. The condition number is defined by the ratio between the maximum eigenvalue and the minimum eigenvalue. You can imagine the more singular, the covariant matrix, if it is more towards singular, it will have a higher a conditional number. It will often result into a worse rate of convergence. And then again, we have a numerical treatment. The way to improve the condition number of such a linear solution is to multiply another matrix in front of it. We call it the precondition. This approach is called preconditioning, because if we imagine if we multiply a P inverse in front of the linear solution, so that we try to find a linear solutions with P inverse K hat instead of K hat alone, then what we are then calculating is instead of the condition number of K hat, now we're looking at the condition number of P inverse K hat. And just imagine, for whatever reason, we can magically find out the P inverse being K hat inverse. And then in that case, then the P inverse K hat becomes identity matrix. Then the condition number is become 1. And it is also intuitively why it makes the conjugate gradient faster, because imagine if we have a P inverse equals a K hat inverse, then we become a V minus K hat inverse Y. Then it is obvious, like with 1 step, so we already can recover the true solution. And of course, that is not doable in practice, but the idea is that people will use some domain knowledge to come up a way to defining a preconditioning matrix, so that as close as possible to the covariant matrix, or the inverse of the covariant matrix.
Cool. There's a quick question about whether or not it has just one optima.
It's a quadratic system, therefore there's only one optimal solution.
Cool, thank you.
And I take some nice examples from Alexander Davis' thesis, which is, by the way, if you want to look into this type of method, I highly recommend look into that. That's a really nice write-up about the conjugated method in the context of Gaussian process. On the right-hand side, he shows the example of solving a conjugated gradient method over a small data set have 415 data point, which is indicated as a blue circle. And the different colored curves are 5 separate realms. And each figure shows the conjugated gradient solutions at a different number of iterations. The iteration zeros are, remember, the V0, I put it there for the previous slide. That is the initial guess of solution, so that you can see it is a pretty not matching the data. And then after a few iterations, like until the iteration 7, it's already more or less covering the data. And after, like say, the iteration 13, it's actually more or less nice Gaussian process fit. Also, I want to mention, one thing I forgot to say, all these colored curves are the posterior mean of a Gaussian process. And another thing I want to mention, just to link to the more practical use cases, if you ever use the library called GPyTorch, it actually have a family of a conjugated gradient method implemented inside. And those methods are based on this particular idea, but with some better designed condition matrix and some formulation of the conjugated gradient. Yeah, let's move on. And so far, that's a conjugated gradient method that allow us to reduce the complexity from n cubic to n squares. But you probably see previously, I already roughly have go ahead.
Just interrupt. There's a question about the last topic. I guess that should quickly be answered before we move on. From Edgar, what is the complexity of the conjugate gradient optimization? Is it basically the number of iterations, and in terms of number of iterations, number of n?
Yes, it's a n squares times the number of iterations, because we typically set a constant number of iterations. Therefore, we usually omit the constant part to say like the complexity of a conjugated gradient method is O(n squared). Make sense?
Is that okay, Edgar? I guess if you still don't understand, just feel free to ask a question again. Cool. And then Andrew asks, is there any circumstance where you wouldn't use the conjugate gradient approach?
That depends on the practical use cases. But one thing you can easily see here is like it heavily depends on the rate of convergence. Heavily depends on the condition number of the covariant matrix. Although we can try to find some preconditioning matrix, but sometimes it may not always work well. So from my gut feeling, if we have like a highly low rank or close to low rank ill-posed covariant matrix, then we might struggle with covariant matrix. But it really depends on case by case. A lot of cases people say you can get away with a little bit like approximate solution, and sometimes if people are picky with exactly fit, and then you struggle. So it's hard to say, because again, this is into another regime that these are numerical approximations. we have to cut where we are satisfied with, and in practical case, it's very hard to know how accurately we really need. So that is a little bit hard to say in practice.
Cool. There's a couple of other questions. I don't know how much time we've got. Is there time to answer a few more before we move on?
Yeah, we can.
Cool. Okay, so someone's asking whether it's available in GPy or only in GPyTorch.
We didn't implement the conjugated gradient method because yeah, it's a bit about the belief that whether you believe we can actually find preconditioning matrix one solve all. In the generally understanding of the numerical algorithm literatures, people don't believe you can find a preconditioning matrix formulation to just solve all problems, because otherwise, like this, if we know P equals to P inverse equals to K hat inverse, then there's no reason we need to solve this problem. So that also during the time we developed GPIs, we also doesn't actually develop does much in that direction. So, but if you really want to try out the conjugate gradient method, I think GPyTorch is probably the best choice at the moment.
Cool, thanks. And there's one more question at the moment. So I'll just read it. It's from Takafumi. Sorry, I just want to clarify. Are you talking about the case where the number of training data n is big, and not for the case where the dimension of training data q is fairly small? Okay.
And currently, in all these discussions are mostly concerned about the n being very big. Q being big will resulting into some practical issues if it is really big. But usually the biggest limiting factor is n, because the n is really the part that gives the cubic complexity, but the q is a linear. So that usually if we can get away with some calculation of q, and then it is not it's less a problem about the computation than the n. So that the discussion so far is mostly around the number of data, not the input dimensions. But if you have a high dimension, that's another story.
Cool. And the last thing I think is about, so I'll read it. The number of output dimensions is a vector, not a matrix. So I guess it's just a single output GP. I guess that's what they're asking. So, yeah.
The model for simplicity, we are discussing so far are all assume Y to be a scalar output. You imagine a regression from one or high dimension input to a scalar output. If we have a vector output, there is actually a number of choices, modeling choices you can do. The typical choices, for example, the default way in GPy, if you put the output to be a vector, it can automatically handle it. And the way it works is that we just assume the different Y's are independent observation following the same covariance matrix and the same noise variance. So that basically different output Y are ID samples from the same prior distribution. Of course, that is one assumption. And there's also other assumptions if you believe those are more suitable for your modeling problem. For example, multiple output Gaussian process. If you're assuming like those, if you believe that the different output dimensions are correlated to each other, and particularly those correlations are important to solve your problem, then you can augment it into even further to treat the different output dimension to be correlated. But yeah, for simplicity of discussions in these lectures, we're only discussing the output dimension to be scalar.
Cool, thanks for that. And yeah, multiple outputs we're discussing later today. So if you want to ask about that, then that's the time. Cool, thanks. Anyway, I'll let you get on. Thank you.
Yeah. And so previously, the numerical routines will bring us from n cubic to n square. But remember the scaling curve things, like n squares is still not going to be fast enough for a big data cases, because it is still going to be quite slow. You can fairly easily noticeable of quadratic scaling. For example, for like those large scale computation, people basically believe that the only thing scalable is actually linear complexity. So then we will take a different routine, a different approach. Instead of like just use a numerical approximation of the matrix inversion, and this time we will look into the model and the inference itself to see like, can we make some trade-off of the modeling choice or the modeling formulation or inference formulation, so that we can result into a more scalable inference result. So first, before diving into the specific techniques, I want to also motivate the general motivation of this family of approach. So the first thing is that we previously are all generally talk about a large data, big number of n, but often if we look at the real world large data, it means like, imagine we have like those industrial use case of like, imagine a e-commerce website that users come to shop and you want to predict certain things, for example, whether user going to buy something, and then you can easily accumulate a data log of the user's activities, even terabyte, petabyte each day. And we want to, of course, to build a model about those user behavior so that we can recommend the right thing to the user. And one observation from such kind of data is that we know that data are not putting it that way. A lot of data does not necessarily means the underlying relations are necessarily complex. And the reason behind that is that, for example, use the e-commerce example as examples. Most of the users, or a lot of users, are probably following a similar behavior patterns. If we ever try to plot those behavior patterns, imagine some sort of histogram. Often what you see will be a power law distribution to say like a large number of users following some common patterns, and then is a very long tails about less common behaviors. So in short, the ideas I want to convey here is that a lot of number of data does not necessarily means the underlying function being complex. It can be a lot of data explaining similar things. And just to mimicking such kind of scenarios, I just create artificially examples about this is a simple 1D regression functions, and I just created a lot of data in the middle and a less amount of data on the two sides. You can see I can artificially generate a lot of data, but the still underlying relation is still simply like this. And in that cases, the additional data may help reduce some noise about estimation, but it does not really make the underlying like function that's really complicated. So that that leads into one consideration that if basically following that reasoning, that basically means like data redundant. And then the immediately reasoning will be, why don't we just subsample the data? And in practice, that will actually a lot of things happening if we do a real world modeling studies. The first thing we will do is, even though we have hundreds of millions of users, we probably will start with like a few thousand or even like tens of thousands to just start with understanding the user behavior. But there's one drawback come with like subsampling our data is that we already previously covered that discussed that the users have usually those power law distributed. So that means like subsampling will effectively reducing the users in the head. But we're also heavily limiting the users in the tail, which means like in those less frequent cases, we are often losing out of those data. For example, if we subsampling a data density following this shape, then we're very quickly we're losing out of the data point at the two ends, so that the prediction or the modeling accuracy of this area with less data will decrease dramatically if we subsample the data. So that we probably want more smarter ways than just subsampling the data. Let's before we go into how to improve from simply data subsampling, first let's look at in this kind of a redundant data scenario for Gaussian process, how does it look like in our Gaussian process inference cases? Because we know the essential component in a Gaussian process inference is the covariance matrix. So let's first visualize the covariance matrix from the previous examples. We know there's a lot of redundant data in the middle. And I just sorted the data point, 100 data point from left to right, and plot the covariance matrix of those 100 data point on the left-hand side, the heat map. You can see those big block of high values indicate that there's a strong correlations inside, in particularly in the middle part. And the other things I show on the right-hand side is that for this 100 by 100 covariant matrix, I calculating the eigenvalues of the covariant matrix and sorting the eigenvalue and plotting them from big to small. It's a typical eigenvalue plot. So the x-axis are the different eigenvalue from the first to the last, and then the y-axis are the value of the eigenvalue. We can see the eigenvalue decrease dramatically from very high value to close to 0 around roughly 10 dimensions. So that indicates that the covariant matrix is a very close to a low rank covariant matrix. So that one way to deal with such kind of covariant matrix may be to just approximate them with a low rank covariant matrix. So that in fact leads into actually a direction of a Gaussian process approximations, which is we try to deliberately construct a covariant matrix approximation to be a low rank. Let's recall that the Gaussian process log likelihood formulation is the log of the multivariate norm of y, zero mean, covariant matrix being k plus sigma square I. And when we talk about the low rank matrix, we're actually talking about the K, which is the covariant matrix among the training data, the prior covariant matrix among those training data. A particular low rank approximations is actually called Nyström approximations developed by William and Seeger from 2001. The idea of that low rank approximation is also quite simple. It's actually very much related to the subsampling idea we just briefly touched. The way the approximation works is that let's first randomly pick a subset of the training set, a subset of a data point from the training set, and then we indicate those, we're stacking those data points together and denote as Z. We are picking m number of them from the data set with n data point. And we know the input dimensionality is Q. So we stack the subsampled m data point, so which will result into Z covariant matrix with m by Q. And the Nyström approximations, we approximate the original covariant matrix K by K tilde, which is constructed in this following way. It is being written as the KZ multiplied with KZZ inverse and KZ transpose, in which the KZ is a cross-covariant matrix between the original training data X and the subsampled the training data Z. And the KZZ is the covariant matrix between the subsampled the data set Z and Z. Therefore, the KZZ is a covariant matrix of m by m, and the KZ is a cross covariant matrix by m because X has a n number of data point and Z have m number of data point. And therefore, you can see like this K tilde still has the shape of m by m because we are multiplied with KZ at two sides. And but we know this is a low rank matrix because the middle part is only m by m, so therefore the maximum rank of such a K tilde is m. And we can simply plug in that into the original of log likelihood, and then that result into approximated log likelihood formulation being in this form. And just a quick check of the Nyström approximations. If we using 5 randomly subsampled data point as the constructing the covariant matrix, to select a random data point to form the Z and constructing the K tilde matrix. And the left-hand side shows again the heat map, but this time for the K tilde. You can see it's still not too different from the previous one. And the right-hand side, we see again the plot of the eigenvalue. This time we see the eigenvalue drop to the exactly 0 at the 5, at the number 5, because this matrix is by definition low rank, so therefore after the rank 5, the eigenvalue are exactly 0. And also another thing we can do is we can vary the number of subset of data point we select, changing from 1 to 20, and we can roughly measure how different is the approximated covariance matrix K tilde versus the original covariance matrix, which is measured by the trace of the K minus K tilde. And the trace term value is shown in the y-axis, and the different number of m is shown in the x-axis. This result is average of like 100 random sample of the subset, so that we can see a smooth curve. And you can see like the error decrease dramatically when the number of m increases. So roughly at m equals to 10, we already see a very small number of trace term, and at 20 is very close to 0 already. Well, previously we already see that if the data have if in the training or in the data set there's a lot of redundant data, it will result in approximately low rank covariance matrix. We can very relatively accurately approximate them with a low rank approximation. And then the second thing is that how can we take a computation advantage of such formulations? If we directly plug the K tilde into the log likelihood into this formulation, if we directly calculate these equations, we don't see any speed up, because we're still again inverting a covariance matrix of a K tilde plus sigma square I inverse. It's still inverting an n by n matrix, but we can play a numerical trick by applying a rule called the Woodbury formula, which allows us to rewrite this structure of a covariance matrix inversion into the right-hand side, which is basically a diagonal matrix minus another low-rank formulations, where the inside is the KZZ plus sigma square inverse KZ transpose KZ. Keep in mind this KZZ is m by m, so the inside is a m by m matrix. So if we plug this formulation into the above equations, this time we will only need to invert this m by m matrix instead of the original m by m matrix. With this, but still for example the y, it's still n vector, so that we can reduce the complexity from original n cubic into nm squared. Make sense?
Cool. Hi, there's a question in the chat. Okay, cool. Someone's answering it already, I guess. Anyway, Simon says, is there possibly nonlinear dimension reduction a reasonable idea? Or are there any known pitfalls? I don't quite know.
I mean, it's the idea about approximate the low rank with PCA or something. And directly doing it does not help, because a PCA or SVD, this kind of a numerical covariance, like those low rank approximations are also cubic complexity. For example, SVD or eigendecomposition are both cubic complexity. So if we directly apply a low rank approximation to K, and then there is no computational benefit. But if when we reach later into more fancy approximations, we will touch like those inducing point approximations. Then instead of doing algorithm like PCA, we can do a bit smarter, like for example clustering or this kind of algorithm to resulting a smarter low rank approximation. But we will touch a bit later.
Cool, thanks for that. That's great.
Cool. Let's move on. We have half an hour. I will try to cover as much as I can. Again, always a bit challenging. And so one thing you may notice that the Nyström approximation, although gives us a computational benefit, but we really doesn't have a control over how does the random data are how the low rank are constructed. It's basically subsampling the data, and then it has the same like challenges we see before with data subsampling, that we will very easily lose out the data in the tail, because if we uniformly like subsampling, then those are the data quite easily will proportionally being discarded, and then we will very quickly lose accuracy in the areas where there's less data. So that's the limitation of the Nyström approximations. We have quite a limited control of where the low rank approximation is being constructed. So then there's further research along this line. For example, the Nelson and Gaussian 2006 proposed the idea about instead of just the subsampling data, let's have the pseudo data approximation ideas, which later refers to as a fully independent training conditional. The idea is that we have the training data X and Y. Let's augment it with some unseen data with output U at an unknown at some location Z. U and Z are those data we don't really observe. We just assuming they're there. That's therefore we call this pseudo data. If we, for the time being, write a Gaussian process distribution jointly of U and Y, we can write them into the following block matrix formulations, so that it become a multivariant normal distributions where the output is a concatenation of Y and U. Mean is again 0, and the covariant matrix become these block covariant matrix structures. KFF plus sigma square I, because we're assuming Y is noisy and the U is noisy free. Therefore, there's no sigma square I there. And the KUU represented the covariant matrix among those pseudo data U, which is calculated by applying the covariant kernel functions over the Z dataset. Sorry. And the KFU are the cross covariant matrix between the X and the Z. Of basically, it's by applying between the training set X and those pseudo data Z. Thanks to the marginalization property of Gaussian distributions, if we take the previous formula with augmented distribution, even though we don't know those are U and U are unknown values, but we can still marginalize them out. If we marginalize them out, they will result into exactly the same Gaussian process prior distribution as if there's no the data augmentations. And further, we can rearrange this joint distribution into a conditional form where the P of U given Z are a prior Gaussian process distribution share the same kernel function, which is basically 0 mean, and the covariant matrix KUU, and the P of Y given U are conditional Gaussian process, which is basically in this particular case over the finite data, it's been written as a conditional multivariate normal distribution. This is again very similar to the prediction equation, because these are conditional multivariate normal. I won't go into too much detail. Yeah, so far the good thing about this formulation is that we have augmented the data, and the original prior distribution does not change, so that we are augmenting the original training data with no artifact. Oh, sorry, I think I jumped. Yeah. But the downside is that there's also no speed up, because if we consider the formulation of if we consider the formulation of this one with some given that, we still need to invert this covariant matrix. KFF is basically the covariant matrix of the exactly covariant matrix K, and because the formulation containing this covariant matrix, so that if we directly try to solve such kind of calculations, there's no speed up. And in the Fitzy approximations, what people do is that then what they say is, instead of taking the full covariant matrix, this one, they only take the diagonal entries of them. So let's indicate this O as the element-wise multiplications, so that we multiply this covariant matrix with an identity matrix, which result basically we only take the diagonal entries. Then we approximate the conditional distribution P of y given U by this multivariate normal distribution. What the special part of it is that the mean does not change. The covariant matrix, the diagonal entry does not change, but all the non-off diagonal entries are become 0. A big benefit of such a formulation is that calculating this multivariate normal, because it's a diagonal covariant matrix, it is much more efficient because we don't have to invert this covariant matrix anymore. And in these formulations, we can further do is that we do not know U, but we can marginalize U out because the PU and the P of y given U are both normal distributions. If we marginalize U out, we result into approximate Gaussian process distributions of y given x and z, which is written in this form, which this is the KFU, KU inverse, and KFU transpose. This is actually the same formulation as almost the same as the Nyström approximations. And here we have the diagonal entries come from the Fitzy approximation of the conditional distribution plus sigma square I of the noise variance. Again, these formulations can be calculated efficiently because we can again apply a Woodbury formula when calculating the log density of this multivariate normal. Apply the similar rules. This time we have A instead of sigma square inverse I because it's a diagonal but not an identity matrix anymore. But the structure follows the same. In the middle, we have a M by M matrix, which is about those inducing points. With these Woodbury equations, we can actually calculate the Fitzy approximations again by M squared complexity. So a bit of summary. The Fitzy approximations allows us to now the major difference compared with Nyström approximation is Nyström approximations are randomly subsample the data to construct the low rank approximation of the covariant matrix, but Fitzy actually constructed based on some pseudo data. So the Z is under our control. We can choose it to be at an arbitrary location. And we also know that if we choose the pseudo data to be the same as the training data, if we plug that equals to x back into the previous equations, we know that fall back into the exact Gaussian process formula because all these approximation canceled out, then we result into the same formulation as the original GP. It basically consider every data as the augmented pseudo data, then we have no information loss. We are recovering a full rank covariant matrix. And also the Z, because we are freely choosing them, we can optimize them with a gradient optimization that allow us not only we can choose them, we can also freely optimize them to be the optimal with respect to the approximation formulations. Also, side remark, Fitzy actually work quite nicely with a Gaussian process approximation called expectation propagations. There is a link with approximation we will discuss further. And there's some, but this also comes with some limitation of the Fitzy approximations. one thing we noticed that remember previously, to make the computational benefit of FITC, we actually approximate a full covariance matrix by a diagonal covariance matrix. That of course introduces errors in the calculation. What the resulting effect is that the better log objective, basically better log likelihood, do not necessarily correspond to approximation closer to the original Gaussian process. This phenomenon actually being studied multiple times in the literature, for example, by Joaquin Candela and Rasmussen, and also Bao et al. A figure in the below basically showing that and the black dot are some data point. The gray solid gray curve are the true mean, and the gray shadow are the uncertainty of the true exact Gaussian process. And the dashed red line are the FITC approximation, the mean, and the solid red lines are the error bar, the 2 standard deviation error bar, and the red cross are the location of the pseudo data. One thing you will notice is the negative log marginal likelihood for the FITC is actually higher than exactly GP. But you can see that the error bar is actually too narrow at the location where they are pseudo data. It looks a bit like overfitting, but it's not exactly overfitting, because we are talking about the approximate inference, but you can see kind of overfitting like behavior. And that leads us to talk about another different approach is related to pseudo data approximation, like the FITC approximation we've seen before. But instead of approximating or change the model formulations this time, we try to keep the model formulation the same, but use a variational framework to actually approximate only the posterior formulations. For people are not so familiar, variational framework, variational inference is a probabilistic inference framework. The way it works is that it well defines a family of a posterior distribution. Usually, for example, these are general notation, do not link that to the GPs. For example, Y is observed data, X is are unknown latent variables. The way the variational inference works is that we will define a parametric family of posterior, typically we denote as a QX, and we will optimize the parametric formulation of the posterior to be as close as possible to the true posterior. So one way to write this lower bound is that we are minimizing this, we are maximizing the lower bound, which is equivalent to minimizing the KL divergence between the variational posterior and the true posteriors. Following that ideas, Titius actually introduced a variational inference approach for sparse Gaussian process. Is basically it's a same idea along the idea about the pseudo data approximations. Again, following the same ideas, so that in these cases, we following the same approach to augment the data. Remember previously, we augmented the P of F given X by some pseudo data U located at some location Z. The P of U given Z is following the same Gaussian process, and this is P of Y given U, conditional Gaussian process. We already, from previously, we already said that this augmentation does not change the original Gaussian process prior distribution. And the way it works is that the variational sparse Gaussian process works that we are introducing a variational posterior for the latent variable in this model. There's actually two latent variables in this model. One is the noise-free observation of the Gaussian process F, and then the other is the value of those pseudo data U. Both are unknown, and we just plug in a standard variational inference lower bound where it is typically written in this form. On the on the nominators are the joint distributions, basically P of Y given F, P of F given U, and PU. And the denominators are Q of F given comma U is basically the joint variational posterior. To get some speed up, Tizet actually proposed a rather special formulation of the variational posteriors. He defines the posterior in these specific forms. Q of F comma U, he defined it as of the prior distribution of P of F given U times with a parametric posterior formulation for those inducing variables U. In this case, this Q of U, we parameterize them as a multivariate normal. Both the mean and the covariance matrix are variational parameters. We will optimize through optimization. Why this formulation is special? If we plug in this formulation into the previous lower bound, so that we basically plug in them in the front of the log and the denominator inside the log, what we immediately notice is that the P of F given U appear both in the nominator and the denominators. So they cancel each other out. And then let's rearrange the log. We separated the P of Y given F out. Then this part, the P of U and the QU with the integral QU in front, we recognize they are basically, that is basically a KL divergence between QU and the PU. It's basically KL divergence between the variational posterior of the inducing variable and the prior distribution of those inducing variable. And the front part is an expectation of the log, like the noise distribution. Is for the regression, we know this is basically a scalar normal distribution. It's a normal distribution with a mean F, the variance being sigma square I. And we still have these two terms in front. It is basically has a integrated with these two distributions. If we put the P of F given U inside, we can result into a closed form distribution inside. It will look like the form like this. It still looks roughly like a normal distribution form with Y, and the mean being the mean of the P of F given U, but because of the P of Y given U have a diagonal variance, so that what will result into like a diagonal variance formulation here. What is special about these notations? This front part actually can be calculated very efficiently because this covariance part is diagonal, and this part we can totally calculate them with the computation complexity of nm square, because these are basically inner product of two vector. The m part are with respect to the k of f u, because it's a cross covariance between the training data n and the inducing variable u, which is m by m covariance matrix, and then the KUU is m by m. So the first terms can be completely computed with a complexity of nm square, and the second term, the KL divergence of u, because u is only m, a vector of m, so that this part is only a complexity of m cubic. So therefore, the overall complexity of this variational approximation is nm squared.
Oh, there's a quick question about, I'm not sure which expression was in, but Simon asked what happened to P of F given U xz as a prefactor to the KL term. So you scroll back.
Say again?
I think he's concerned about the first term in. So he wrote, what happened to P of F given U and X and Z as a prefactor to the KL term?
He is concerned about this probability in the KL part. note that this integral over both f and u, and all the remaining part of these things is only concerned of u, and the only part regarding f is p of f given u, and we know this is a distribution. So conditional on u, the integral of p of f given u is always 1. That's why it disappeared.
Cool, thanks for that. Yeah, great.
Yeah, this is the nm square. And one further note on that, we actually know that the optimal parameters for the QU formulations is actually closed form. Previously, we explicitly formulate them as a variational posterior with mu being the mean and the sigma, capital sigma as a covariant matrix. These things we actually can calculate in closed form. I won't go into the detail of the equation here. It's a little bit complicated, but that is completely doable. You can take a derivative with respect to lower bound and then easily find the optimal of the mu and capital sigma. And the second thing we can do is we can plug in the mu star and the sigma star back into the previous lower bound. That will result in the tighter lower bound because the optimizer does no longer have to optimize the mu and capital sigma anymore. Whenever the gradient optimizer changes the other still remaining variational parameters, the mu and the sigma are automatically optimal. So that makes the variational bound always tighter. And the resulting lower bound looks like actually this form. It's again interesting because the similarities. If we look at the first term, that is exactly the same as almost exactly the same as the Nyström approximations. Being the difference being that the middle part is no longer a randomly subsampled data point, but those inducing point we choose of which the locations we can optimize. So that we are basically calculating the middle part of some covariations over the locations we specify as Z. But overall, it still forms such a low rank formulation. And we have a trace term to compensate as a variational lower bound. The overall complexity, after we plug in the optimal mu star and the sigma star, are still nm squared. Because again, we can apply the Nyström approximation, and here we only do the trace of the covariant matrix, although this is n by n, but the diagonal of n by n is still n complexity. So the overall complexity of this tighter version of the lower bound is still nm squared. A few observations of this more newer formulations. First, this is a lower bound, but not a log PDF. Exactly because the trace term, if we exponentiate the variational lower bound and integrate it over y, the integral will be smaller than 1 because exactly the trace term. Unless the trace term is 0, then it becomes exact. That becomes the lower bound becomes exact, and therefore the lower bound of the log PDF becomes the exact PDF. And the second thing is that a benefit of rewriting this whole thing in a variational lower bound or the variational inference framework is now the location of those inducing those pseudo data, those inducing variables, the location of those inducing variables are variational parameters now. One property of a variational parameters is that we can freely optimize them. That will not lead to any overfitting. It will just find the best variational posterior formulations under the family of specified variational posterior formulations. We can very easily observe that that effect. We can arbitrarily increase the number of inducing points for even a very simple regression case like this. This case, we only have 8 data points. We can arbitrarily increasing the number of inducing points. That will not lead to some sort of overfitting, but rather it will the approximated Gaussian process posterior will be the same as the true Gaussian process posterior. at least under the area where they are inducing point. And some remarks also about the Fitzy versus Variational sparse Gaussian process. The major difference between them is that the Fitzy approximations, it changed the model, while the Variational sparse Gaussian process keep the model the same, but defined it as a variational inferences. That result into some phenomenon is that the variational inference will not overfit with by optimizing the location, but Fitzy's approximations, it may not the optimized inducing location may not necessarily lead to optimal posterior. But there's also price we pay with the variational approximation. If we have too few number of variational parameters, then things that commonly happen is that we will observe something we often describe as underfitting, so that the resulting function inference result are overly smooth compared with the true data. That is because if we look again at the formulation of the variational lower bound, L, is basically the marginal log likelihood minus the KL divergence. Because in these cases we are optimizing the kernel parameters, so that we can changing the both terms, so that one with a limited number of variational parameters, the variational inference can maximize in the lower bound by either minimizing the KL divergence, which makes the variational posterior closer to the true posterior. Alternatively, it also can maximize in the marginal likelihood. So the way it end up to be is that it will find the kernel hyperparameters can both suitable for a limited number of inducing points, that it will smooth out to cover the existing data as much as possible, which often leads to overly smooth the inference result. So we sometimes describe it as an underfitting, which is also quite a norm for variational sparse Gaussian process. Yeah, that part I won't touch. And very quickly, not much time, 3 minutes, but I will very quickly run through this part. So far, what we touched is that with either Fitzy and the variational sparse Gaussian process, we reduce the computational complexity from n cubic to nm square. N is n is the number of training data, so it's linear with respect to the number of training data, but the cubic with respect to the number of those pseudo data. But one challenge of that one is that you can see that is still one equations. And it's if the data is very, very big, we still have to calculate those whole variational lower bound in once for every gradient optimization. That may be very, very slow. And so that a way deep learning to make the inference fast is actually doing mini-batch training. So at every time, instead of looking at the whole data set, but rather looking at a small subset of the data set, so that every time making a gradient move less accurate, but broadly towards the correct direction by accumulating a lot of small gradient steps, so they overall canceling the error of from each other, and then move towards a much quicker as a result towards some solutions. And how can we do such kind of a mini batch learnings for Gaussian process? If we directly look at this lower bound, the trick of mini batch learning from deep learning is not applicable, because the one essential component or essential things the mini batch training relying on is that the loss need to be written as a sum over different data points. Therefore, we can subsampling the big data set into a smaller one, we are resulting an unbiased estimate of the gradient. variational sparse Gaussian process formulation cannot be written as a sum over data point. But Hessman et al. 2013, they discovered that if we take one step back, if we do not find the optimal QU, but leave the explicit formulation of QU formulation. QU this time is a multivariate normal distribution, and the lower bound looks like this formulation. This particular lower bound actually can be written as a sum over data point. The reason being that, for example, using a regression as examples, for every data point, we know the noise distribution is like a Gaussian distribution with diagonal variances. It is actually, if we have a log PDF of it, we can actually written them as the sum of the log PDF of individual entry, basically individual entry of the vector. And if we plug this thing into that expectations, we actually can result into the first term being a summation over the data point. So that allows us to build a mini batch approximations by approximate the summation over the whole data set by a summation over a small mini batch. And the right hand side terms are data independent, so that we just have to accordingly rescale the value of the carrier divergence, so that this becomes a variation lower bound for mini batch training. And we can just apply stochastic gradient descent method to these formulations, and then we will result into a mini batch training algorithm for Gaussian process. Yeah, these are some results from the paper. I didn't have time to run through them. Some very quickly, pros and cons. The stochastic, we call the stochastic variational Gaussian process, which basically mini batch trainings allows us to further reduce the computation complexity from nm squared to cubic m, because this time instead of go through the whole data set, every gradient step we take only a constant subset of the data. Then the caveat of this approach is then we have to explicitly parameterize, keep the explicit parameterization of the QU. That is actually not insignificant, because if we have m number of inducing variable, for example, the covariance matrix formulation, the capital sigma is actually have an m squared number of parameters, so that the overall number of variational parameters compared with the previous sparse Gaussian process formulations, the number of variational parameters increase from the m into m squared. That makes the gradient optimization much harder. On top of that, with a variational sparse Gaussian process, we are usually using approximate second order method like LBFGS to optimize, which actually can find a good solution with tens of iterations. But for a mini batch training, we have to rely on stochastic gradient descent optimize like Adam, and that usually take a much longer to converge. And also sometimes initialize the QU is a bit challenging. Okay, I will stop here. And I think I've been running out of time. Michael, do I have time to have some few questions, or if not?
Okay. Well, I guess we could just do a couple of really quick questions, and then we need everyone to have a break as well.
Yeah, cool.
So somebody asked earlier, how can the approximation? So they were talking about. I think they weren't talking about the mini batch one or anything, just the original one. How can the approximation help in Bayesian optimization? So they're worrying about where we can decide what data to select, like for the, I think that was when they were like as inducing points as it were, and to avoid redundant data. So they were looking at like, I guess where they can use Bayesian optimization to choose the data. And maybe that's sort of more general question about like, where to place
you can, although it depends on label formulations. And in some standard formulation, like the Gaussian process regression cases, we actually quite conveniently get the gradient with respect to those input location of those inducing variables, then directly optimize together with a gradient optimizations is actually quite convenient. We can quite easily get a good set of a variational like the inducing point locations. But there may be some cases that is not doable. Imagine the covariance functions is, for example, some structural space. There's just no gradient available. Then in those cases, yes, Bayesian optimization actually can be handy there to pick the location of those inducing variables.
Cool, thanks. I'll ask one more, and then maybe the rest can be in the
in the afternoon.
Yeah, in the afternoon, exactly. So David asked, what approximation approach would you recommend in practice, right? So there's different methods. So if there are several, for which use cases? So it's a bit of a big question, but yeah, which method would you use for what problem?
It really depends on the models. In these talks, I only covered a very, very simple model. It's Gaussian process regression. If you are really only concerned about Gaussian process regressions, typically, if I have a not too big data set, I will go, for example, if it is really small, of course, exactly GP. If it is a bit bigger, like tens of 1,000, I will use variation sparse Gaussian process because it's just quick to converge. And if it's really, really big, I cannot really do the gradient optimization iterations with the whole data set. I will just go with the SVGPs. All of them are quite conveniently available in multiple GP libraries. We actually will talk about them in the workshop. But for regressions, these are actually quite reliable choices. But for more complicated models like classifications, for example, non-Gaussian likelihood, people will talk about this, and these will probably lead to a different choice of the Gaussian process part as well.
Cool, thanks for that. Yeah, that makes sense. Right, I realized we're completely out of time, so I think maybe I'll try to write down all these questions and bring them up in the afternoon session. Thanks, cool. Zen-Wen, that was fantastic. I covered so much stuff there as well, like the whole history of this problem. Right, just to let everyone know, so yeah, we'll have a break for a few minutes, and then at 11 o'clock British summer time, we're looking at non-Gaussian likelihoods with ST John, and then in the afternoon, there's the lab sessions and the roundtables at 2. Okay, and then we finish off looking at multiple output GPs at 4. So thanks again, Zen-Wen. That was fantastic. That was really interesting. It's good stuff. Right, I'll see everyone later. Yeah, everyone get a coffee and have a break. Cool. Thanks, Zen-Wen, again.
See you.
Bye, everyone.